Hello and welcome to the first part of the audio and visual presentation part of the CICS TS4Z VSE storage violation education. I'm going to start this off with just a quick look round the CICS and VSE side of things. What you're looking at now is the console for one of the Hersley VSE systems, and I've got my CICS system running in partition G1. The back of the presentation material discusses how to set CICS up in the best way to reduce the potential for storage violations or to get dumps out or whatever. I'm just going to go through a few screens just to show you from a sort of real world point of view how things look like. It's always difficult to do this in just standard presentation material because you can't see things happening in front of you. So I'm going to explain a few things in terms of the setup. But firstly, what is a storage violation? Well, one of the problems in any environment, whether it's batch or CICS, is that programs can trample over storage that they shouldn't do. And arguably in a CICS environment, that's potentially more problematic because you've not got one program running like you have in batch, but you've got multiple programs running. So CICS has a mechanism for detecting the possibility of a CICS program modifying storage in a way that it shouldn't do. It's not idiot-proof in terms of checking, but it's better than nothing. Basically, what happens when you or CICS internally or LE internally requests storage for a task, a get main request will be issued, and CICS will find an amount of free storage that matches your request, rounded up to a multiple of 16. And then it will put a little eye catcher, an 8-byte eye catcher called a storage crumple zone at the beginning and another one at the end. So the allocation that is requested of CICS will be rounded up to a multiple of 16. Another 16 bytes will be allocated, 8 bytes at the beginning, 8 bytes at the end, and in there's a constant that is that says what type of storage it is and what task owns it. And if somebody walks over that storage, CICS is able to detect a storage violation. So an inappropriate modification to part of the storage allocation will cause a storage violation. An inappropriate modification to storage within that allocation won't be detected by CICS. The storage violation is detected when the storage is free-mained, and when that happens is depends. It may happen because an internal or application requested except CICS free main has been issued, or it could be that it's detected when the task terminates and CICS is getting rid of residual allocations that haven't been free mained. When it's at the end of task, you get a code 0F0C, and that's arguably the most difficult to resolve because the program is finished and whoever allocated the storage has probably long since made the damage. There are other codes, a 030B and a 0D11 that are shown. That means that this was an explicit or internal free main before end of task. And basically what we do here if you open a problem with us, is we'll go through the dump in a prescribed way, which is described in the presentation material, and we'll see if we can identify which program it was, perhaps where in the program the storage was allocated. We'll find the area of storage or areas of storage that are affected, and we'll pass all this information on to you, or at least some of it. We don't have the source code for the applications. We don't know how the applications work. The best we can say is, the storage has been overlaid here. It looks like it's a bit associated with this program. And basically, guys, it's over to you. Now, look at the dump, look at the storage, look at the code, and figure out yourselves what's done the damage, because we can't do that. All we can do is point you in the right direction. Sometimes pointing you in the right direction isn't enough, because perhaps the damage was made just so long ago with this complex transaction that you're running that you've no idea what happened when. And if you come back to us and say, well, I'm sorry, but we can't figure it out, can you help us anymore? We'll say, well, try the storage violation trap. The storage violation trap basically finds the problem earlier than would otherwise be the case, which will help you get closer to the point of when the error was made. It won't find the actual instruction that caused it, but if it can point you to a position in the transaction execution that is closer to where the damage was made, it will make your life a lot easier. Now, some storage violations we get are actually quite complex and would be beyond the scope of people who don't have access or the appropriate knowledge to the CICS code to find out what's going on. I mean, it could be it's something strange in CICS. It could be that it's in another product that's running under CICS. So the original idea of the presentation is to give you a fighting chance of solving a storage violation yourselves. It's not. Sometimes it's easy, sometimes it's not, and the presentation at least gives you a process. But just so you can visualize what we're asking you to do when we say, yeah, can you get it again? But when you do that, do this. I'm just going to show a series of screens. Now, CEMT has got some things in. We might give you some CMT commands to use. Now, I've just restarted this CICS system with a cold start, so everything's back to as it is in the sit and sit overrides. Now, storage violations create CICS system dumps, and these are all based on an Abend code, which is 2 alphas and 4 numerics. So a storage violation Abend by default is an SM 0102. CICS has a system dump table which tells it how to handle things when a system Abend occurs. And initially, after a cold start, it's got nothing in to say how it does things. So it works according to defaults, part of which is a CICS hardwired default and part of which is a sit override. Now, sometimes we'll say to you, can you issue this CMT command? And the magic words will read something like set SYD, then the system dump code like SM0102, add it to the CICS dump table. And if it's not already, sys means we want this to take a CICS system dump, and max1 says we only want one of them. Now, if you get a storage violation, CICS will actually effectively internally do that, but the max number will be according to the sit parameter SYDU max, which a lot of customer's set to 1 anyway. So this is typically what you get from storage violation based on CICS internal defaults and the dump options. Now there's a second storage violation, Abend code in SM0103, which is to do with storage violation trap. So we might ask you to set that one as well. I mean, what you don't want to do on CICS VSE is capture too many system dumps. They are a horrendous overhead in VSE, especially if you've got a busy system running sort of 100 plus transactions a second. They make a real mess of things, and that's actually not CICS' fault, it's VSE's fault, because the dump routines on VSE is horribly slow. Sorry about that, VSE, but that's just the way it is. If you do inquire system dumps, you can now see the current setting. Okay, so basically I've primed CICS with settings to say, yeah, please handle the 2 storage violation events with a CICS system dump, but by the way, I only want 1 of each. Thank you. Now, another transaction that we'll ask you to play with at times is CETR. And CETR allows you to play with trace. For example, here we've got a good customer, because that's me, and I've set CICS up to use 4 meg of trace, which is the minimum we recommend. We might ask you to increase the trace table size either by CETR or through a set startup override, TR tab SZ, a value in K. Sometimes even 4096K isn't big enough to contain all the trace data we need. The CICS trace table is in 31-bit VSE partition get this. It doesn't come out of the EDSA lim value. We need trace active in order to solve a violation dump, and so would you. And most customers normally work with CICS running standard level trace 1. Now, sometimes we'll ask you to change the trace settings, and if we go into F4 here, you can see that CICS has a whole series of different component level trace settings. If you want to find out what they mean, go to F1. But we may ask you, for example, to set AP 1, 1-2, 1 and 2. As you go through higher levels of trace, you get additionally more detailed trace information, which we may need to solve the problem, whether it's a storage violation or not. For example, if you've got a TCP/IP related problem and you're using TCP/IP services, say for CICS web support, we may ask you to set up socket 1 and 2 levels, because the socket 2 levels can tell us a lot about the socket request. I mean, I wouldn't normally bother with AP 1 and 2 for storage violations, but we might possibly ask you to set exec interface level 1, level 2. Level 2 exec interface gives you similar-ish information as you get out of CEDF for an application exec CICS request. It can be very useful, and although we don't need it here, if you've got vSAN problems, level 2 file control trace has got some very interesting vSAN related information that we can use to help solve it. So we don't actually need those levels here, but I just wanted to point you at the facility. And if you page forwards, you'll find that there's a whole series of different components. Now you can set these like AP1 or EI 1 and 2 in SIT overrides, and we'll normally give you the option to either use CETR or provide the sit override. I mean, the sit override for EI 1 and 2 is stntrei equals open bracket 1 comma 2 close bracket. I'll leave that set and we'll come out here. So I've changed the trace table size so it's now 8 meg. I've modified a component level trace setting, and I'm now going to come out of there and I'm going to create a storage violation dump. Right, to check on the console, all clear, that's good. Now I've deliberately made a change to one of the programs invoked by the stat transaction to cause a storage violation. Incidentally, node and user ID, I use a VM system for my day-to-day work, and we also use a VM system for handling customer problems. We don't use native facilities on VSE to look at your problems, basically, because, well, the secure VSE systems aren't configured for it, and I think I'd probably resign if I had to use ICCF for solving problems in dumps. Right, clock goes on, which is bad news. Oh, it printed. Let's see what's happened here. Oh, okay. So here's our storage violation. We've got a code 030B, which is telling me, because I know, and I've read my presentation material recently, a 030B is either an explicit or an implicit type 3 main request. So it's not end of task. A 0F0C would be when CICS is tidying up after your task or transaction finishes. Okay, so we've taken a dump. Let's go back to our CICS screen. Let's come out of there and clear that. Oh, it's interesting. So we started off with one storage violation. Oh, and then we got another one. That's interesting. So we got a storage violation dump when the task issued a free main, and now we got another one, 0S0C. So it's been detected again. That's interesting. Yeah, sometimes, although this is a bit of an obscure case, sometimes you do get multiple storage violations from a problem. Now that could be because just the way that CICS works, or it could be multiple bits of storage have been modified and it's caused more damage than you think. But in the second case, it was detected at the end of the CICS task, so that's a 0F0C, and you can see the dump was suppressed. So we didn't get a second dump. When you get problems like this on a CICS system, it's normally the first dump that is most important. Sometimes the second and subsequent dumps don't really help us that much. By all means, send them all in, but you may find that we only end up looking at the one and leaving the others. So that's what a storage violation will look like on the console. Now, we may come back to you, or you may try and do it yourself and then find that you really can't figure out what's going on. But we need to get closer to the problem. And if you're working with us, I still can't spell. If you're working with us, we may say to you, well, you come back second time saying to us, well, I know you gave us that information. You gave us that information, but we still can't find it. Please CICS support. What can we do now? And we say, okay, turn on the storage violation trap. This is what you type: CSFV debug chuk stsk equals all. That's interesting. It's just found one. Okay, I don't know how it managed to find that, but that's interesting. This is a slightly unusual situation, but what would normally happen is that you'd enable debug, CSFE debug, and then at some later point in time you would get an SM0103 Abend dump which you send to us. Now, because this is kind of a setup job here, it's actually detected at an earlier stage than I would normally expect. But basically, if you enable the storage violation trap, it will fire off an SM0103 Abend, and it'll actually disable itself. You can see from the message, the DFH SM0103. Can you see where the Abend code comes from now? It's part of the message. Storage violation trap 0932 has been detected by the violation trap. Trap is now inactive. Okay, so it'll only fire once until we activate it. Now, the storage violation trap is an overhead. If you use check STSK equals all, what you're telling CICS to do is, at an appropriate point in the execution, which is immediately after an application issues an exec CICS request, and immediately before going back to the application, CICS will check the storage of either every task in a system, which is quite an overhead, or the current task in a system. Now, if you say check TSK equals all, it is a noticeable overhead, and I've seen it increase response time by a noticeable amount, because basically if you've got like 200 tasks in the system, each of which has 10 storage allocations, that's 2,000 allocations are checked at the beginning of exec CICS processing within CICS and at the end. And if you add that lot up, for every exec CICS request, there's 2 lots of checking of every storage allocation associated with the task. It adds up. Check STSK equals current is much less of an overhead. However, there's a downside. It can create a false positive. Now, a storage violation can occur because task A has modified task B storage. I've seen that happen. And so task A goes off and does this, then finishes, and then task B collapses at some later point in time. If you can't find it and you want to set up the storage violation trap, check STSK equals current will find task A's modification of task B, but it will tend to imply that task B damaged itself, whereas that's not the case. If you use check TSK equals all, it'll find the problem hopefully sometime within task A processing and not in task B. So check STSK equals all is the safer of the options, and you may just need to put up with the overhead. It's as simple as that. There's nothing worse than getting a false positive and saying it's the program running as task B, and then you spend days trying to find it and you can't find anything when it was the program running under task A that did the damage. So that's a brief introduction to the sort of setup of a CICS environment and what things look like from the CICS point of view. I hope you find that interesting. I'm going to stop this now because I want to discuss the analysis of a storage violation dump in a separate session. Bye for now.